Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. So in this video I'll be talking about linear elastic foundation, basically elastic reaction on beams. This is a requirement for an idea I might tackle in the future, which is basically about stiffened raft foundations. I'm also thinking about raft foundations where you have some increase in thickness below the columns. This is yet not being done in Autodesk Robot, and I'm thinking about that, but I'm still struggling in my head to find a way to model those things. So, of course, I'm talking about elastic foundation, and I'm not talking about rafts this time. I'm only talking about beams, so it's going to be a short video. However, if you want to take a look on how to analyze rafts using the flexible method, please feel free to take a look on the video linked above. Now, for this, I'm going to basically assume a structure that is made out of only beams on ground. So your walls are carried by beams on ground without rafts. Later, I might include some rafts. With that being said, well, let's take a look. So I will make me a very simple structure that is, I don't know, maybe a 3 by 3 meters large. This is a symmetric structure, but of course you can also do a non-symmetric structure. So x0, 3, 6, and 9. So I have a 3 by 3 each 3. And the same for x. And the z, I'm going to use it to 0 to 3. If you apply that, you get a box like this. That seems to be okay. I'm gonna apply me some columns here. So I just click me on column, simple reinforced concrete column, a 300 by 300 millimeter column. Of course, that's just a placeholder. I'm not intending to talk about columns today. Now I just basically apply my columns here. My idea is I want to talk about different foundation options for this. So I'm applying me some columns like this. And, well, maybe the columns in the center I should apply. It's quite easy. Now, those are 100% symmetric. You will never see structure like this, having perfect symmetric columns, but I want to explain them now. But that's not the point, so let's get over with it. I'm not going to bin anything at the bottom. And I was also going just to apply me just a concrete slab for the sake. It's a flat slab just for the sake of analysis. I'm not interested in the analysis of those slabs, but I'll just basically give me a slab with a force just to show some sort of force transfer. So I'm just applying 10 kilonewtons per meter square. This is just a thing. Now, if you run the analysis, you should get instabilities because you have zero reactions, zero supports, which makes sense. Now, of course, you could just basically go quickly and do a pin support here just to make a quick check and make sure that the structure behaves exactly as it is supposed to be. So I'm pinning my structure, running the analysis. This is not new. If you are a follower of this channel, you know that this has been covered in multiple video tutorials before. So yeah, we have our structure. Just to make sure, I'm just checking my results very quickly. If I see maps mx, I should see mx. Perfect. My. The slab is analyzing, I think, okay, well. If you go to our results, diagrams for members, I'm just checking if everything is exactly as it's supposed to be. I think yes. So yeah, our structure is good. All right, so fantastic. Now let's continue with our structure. Now here, the assumption of pins means that you're assuming a foundation below the columns. Now, there are multiple ways of doing foundations here. One of the simplest ways is to make a spread footing below each and every one of those columns. Another one is for small structures to make a raft foundation. But there are two possible types of raft foundations. The first one is basically a constant thickness raft. And this was covered before in the video that was linked above. And the second type is having beams. Now, the second type is also important because you might have some loads from walls on the ground directly. So, well, let's do this. Let's do some beams here. Now, of course, I'll just draw me some beams here. The beams are 200 by 400. It should make sense. Those should be stiff enough to carry that kind of structure. So I'll just quickly do that. I'll beam everything. Now, do you need to beam everything? It depends on your assumption in your structure, to be honest. But I'll just go and beam everything. So yeah, well, I have my first one. I'm going to video edit this. All right, so I just quickly modeled my beams and ran the analysis. Now, don't get me wrong. This is incorrect. The analysis you see here is incorrect. And I will talk about this in a moment. Before I talk about this, I have my beams. Let's assume that everywhere there are walls on the ground floor. Now, this is not always the case, but I will just put my walls above the beams. This makes sense because the beams can carry actually the walls. So I'll just quickly put me a load on the beam that represents the wall. I'm just gonna put me a 1 or 2 kilonewton force per meter. This is just an assumption. I'm not really putting any calculations into my mind here, just putting some values. I'll apply this on all the ground beams, and now I have loads on the ground. Wait, what? I think I messed up my sign, did I? Let me just quickly check. Loads, load table. I think I put 2 instead of -2, right? Yes, it's 2. So I click negative here, hit the enter key, close, and check if the load is going correctly. Yes, it seems the load is being corrected. So if I run the analysis now, this is incorrect, by the way. The assumption is now still incorrect. You see a continuous moment diagram on the beam as if the beam is being carried by the columns and not doing anything in terms of carrying the structure. What I'm trying to say here is that this beam is basically flying on air. There is no soil below it because I have not defined it yet. So this is so far incorrect, but at least we are getting somewhere. Now, of course, if you remove the supports from here, you will get an unstable structure because suddenly nothing is carrying your structure. So let me show you. If you remove the pins, run the analysis, this is an unstable structure because the structure will fall down. You see, it's in UZ, it's falling down. Fine, perfect. Of course, I get some gibberish in moment diagrams. This is absolutely expected. So I'll go back and pin that stuff. So far, so good. Alright, so, well, once again, we are not finished yet. Now, of course, notice my loads are just placeholder loads. My point here is to explain how to let beams carry your structure. So if I remember correctly, back in the day, it was something called about elastic foundation. Let me just check. Ah, there we go. It's member elastic ground. Now, if you click on member elastic ground, you get this thing. And you see ground 1. Well, I'll add my own ground. And let me call this, like, I don't know, my soil or something. Now notice there is a button called elastic foundation coefficient, and you will see a very similar definition for the elastic ground as has been explained in the raft foundation video. So please refer to that. Now I'm gonna select clayey fine sand, which will basically, of course, it's a beam type foundation. It's a continuous longitudinal foundation, and now you can basically apply some dimensions here. Now, of course, the estimated foundation load is not 100 kilonewton per meter. I think it's less. Of course, this will also carry the columns, so you need to know what the load is based on what loads you have here on the columns. Now, how would you do that? There is only an approximate method to do this. By that I mean, well, you click on reactions, results, diagrams members, reactions, FZ, and just take a look on the values, click descriptions. I think I missed that. 177, 177, 44.7, 44.7. In total, you have around 400 kilonewtons of reaction, and those 400 kilonewtons of reaction are basically applied on a 9-meter beam. This is an approximation, of course. 400 divided by 9 is around, I don't know, is around 45 kilonewtons. In addition to 45 kilonewtons, you have the wall load, which was 2, which means you have 47 kilonewtons. So I'll apply here a 47 kilonewton per meter load. As for A, well, B is the width, and the width of the beam here, the width of the foundation, is basically the width of the beam. Now, I assumed, I think, 200 by 400. This is just a placeholder. Of course, you need to be able to do it yourself. 200 by 400, so my B is 200 millimeters. It's in meters here, so 0.2. Now, as you can see, with 0.2, it doesn't calculate. So, of course, this is a strange thing because A was not inputted. And since A is not inputted, of course, the question is, what is A? I thought B is 0.2, but I'm thinking A is maybe the length of the foundation, which is the beam here. I'm not sure, so the easiest part is to click on Help. If you click on Help, well, you see Autodesk Robot's help file. You go down to check because it's important to learn how to learn. So let's take a look. Continuous footing with dimension A. A is the continuous footing length. B is the continuous footing width. Okay, which means that basically A is the length, which is 9 meters, and B is the width, which is 0.2. I think now I have my coefficient, which is this in kilopascals. So I click on that, OK, and close, and now I have my foundation elasticity. I can use this, so I'll just add it, and I can use this to elastically hold my elements to the ground. So I'll select those and apply that. Yes. And there should be a symbol. Do I see a symbol? There is no symbol. Huh. Okay, how do I know if it's correct or not? Let me just check. Let's click on this. Well, let's take a look. Yeah, there we go. Elastic ground. I think there should be a display option, so let me just quickly check. Members. Well, there is no, right? Oddly enough, there is no foundation elasticity. I'm surprised. I thought I would find a symbol. Yeah, it seems this is one of the regions where not many people go into. Anyway, like, check out if you find it. If you find it, tell me about it. Fine. So if you run the analysis now, this is still an incorrect model, but I will run the analysis anyway. If you go to results moments or diagrams members, you see that nothing has changed yet, which is odd, although you have done your elastic moment and elastic ground. Well, let's now take those things and remove them at all. I want to remove all reactions. I am expecting this to be unstable because I don't think we have any reaction in the X or Y. We only have reaction in Z. So if I run the analysis, I think I will get UX, yeah, UY, okay, and fine. Now, first things first, I have UI instabilities. I ignored that. I will tell you why in a moment. Let me recap now. First of all, let's add back the pins, just to add back the pins. Let's add the pins back. Now, if you have the pins, then you would have a strange simply supported beam because there is, yes, you added pins, but there is still the continuous rigid connection between the column and the beam, which will in turn transfer the moment of the column onto the beam, and that's why you have this strange odd diagram. Of course, this is incorrect because it's either this or that. You cannot have supports and have elastic foundation. It's either you have elastic foundation that carries the structure or you have supports that carries the structure. You cannot have both. So if you take those things and remove them, let's remove the supports. Now I'm still predicting instability because the supports are in UZ and there is nothing in UY or UX. Now, truth to be said, our structure should not be unstable because there is friction. Like, this is some of the tests you would do on a structure. Also, our structure is embedded in the ground, so it's pretty hard to move it. Also, having a beam like this means that it anchors itself into the clay because the surface of the clay, like, how do I construct this? The surface of the clay would go up to like height of beam minus 20 centimeters because you're going to put your slab here or your raft here. So I'm kind of not convinced that this will move. But of course, Robot doesn't see this. Robot doesn't understand those practical ideas. Let me repeat that. When you implement this, you would dig your trenches and basically cast your concrete and fill the soil until 20 centimeters below the surface because you want to cast the rest of the concrete with your raft. So this will never move in the, never say never, you have seen Turkey, but this should not move in the X and Y. But Robot doesn't see that, so we need to convince it of this. So I'll just put me here a new support. I'll call it, I don't know, like stab for stabilization. And the only reason I'm doing is because I'm going to apply UX and UY. That's the only thing I'm doing it. So I'll add this as stability and use it to hold any arbitrary point. There is no certain point I want to hold in place. So I'll hold me any arbitrary point. And I don't want to hold all four corners. If you hold all four corners, if you hold them all, then you stop the movement in X and Y. And this is incorrect because the structure will move in X and Y. It might expand or contract based on the structure. I don't know. So let me take a run here and just see what happened. Now it's stable, and you get the usual elastic foundation moment diagram, which is basically an inverted slab. So if can I invert this? I don't think I can. I can't invert it. But this is like the inverted slab. And I think I should be able to see the elastic foundation reaction, right? Results, diagrams for members. Oh, there we go. The KZ reaction. If you click on that, you see the elastic foundation reaction, and it's exactly as it's supposed to be. Maximum below the columns, and tad smaller below the beam. Fine. Now, this is not what our dear subscriber Donald Khani has mentioned. This is a different structural system in which you are basically carrying the structure on beams, and this is, well, useful for maybe, I don't know, maybe the smallest of structures, and you still have to pay attention to your soil bearing capacity. Of course, this is something I want you to check and check how you deal with this at your at your design. The thing I want to mention here is that beware, your maximum soil pressure is 28.63, and this is, I think, in kilonewtons, I think, per meter. And you will have to, this is incorrect because this is a longitudinal pressure. You have to find it in equivalent kilopascals to compare with the bearing capacity of the soil. And in this case, you would need to multiply or divide or whatever by the width of the beam. This is something I will leave for you. Now, this was not the question of our dear subscriber Donald Khani. Our dear subscriber Donald Khani was asking about having a combined raft and beam foundation. A stiffened raft, he called it. And for that, I will basically do this. And I'm not really sure. I have to double check this at home and do some calculations. The quick idea I just want to give as food for thought. This is not really what I will recommend because I don't have yet gathered enough information. But food for thought is that I'm gonna add me a shell, 200 millimeters. Of course, I can't make it smaller because I mean you have beams, so I can make it smaller than 200. But that's beside the point. I think I have a raft. Do I? No. So I'll define me a raft here. I'll say TH200R. I think I'm gonna make it 150. I don't know. It depends on what you are doing here. I think having beams. By the way, having beams means that you do not have to make a punching shear check on the raft because you're assuming that the punching shear is being carried by the beam shear. So you have to make sure that the beams don't break. Anyway, I'll go now for this and go to foundation elasticity. And well, I go to elastic foundation. And now I need, of course, you need to define the very same soil because it's impossible to have two different soils. This time I'm gonna leave this to check at there was a video about rafts, so I'll leave that for you. The raft here is 9 by 9, so there we go, 9 by 9, and it should be calculating. What about the pressure? I don't know. You need. Okay, let me just check this very quickly. What do? I go to loads. I go to results, maybe reactions. I click on that and take a look on the reactions. So that's the sum of reactions in FZ, 1574. Now this is divided by 81. So having a calculator on my side here, I just take my calculator. This gives me around 19.4 kilonewton per meter square. 19, so let's put 20 here. And what else do I have? Well, 9, and the soil is the same soil. And well, I think we have our kilonewton per meter cube here. I'm surprised it's different, but well, you should check the help and check out how this was calculated. There is a theory behind it. Now, notice that this is a calculator based on robots. If you have your own code, then you can calculate your stiffness factor based on your code and then add it here. This is on you. Now, I'm not going to put any Kx or Ky because I already have stabilized the structure with my little support. I'll add that. I'll add this now and close and use it. So thickness 105. So I have a rectangle now, and now I'm going to add me to this. I'm going to add me this raft. And now I have a combined raft and beams. This is not a final version of what I want to do. This is just food for thought. It may work, it may not work. Now, first of all, as expected, the reactions on the beams went down because now you have a raft that helps out. That's number one. Number two, if you go to results and click on maps, not members, results maps, you can select the soil reaction key and see the soil reaction on the raft itself. Now the finite element mesh is kind of big, and that's why the forces are not really that that viable. But you can see that it makes sense because you have some stress concentrations below the central columns and less stress concentrations outside. And you can now, that's the idea of our dear subscriber Donald Khani, you can now design each and every one of them alone. If you click on the beam, which is gonna be your stiffness beams in the raft, then you can basically go to results and design them. You can check out the videos about designing beams that will be linked above. And of course, you can also check out the slab and see what, of course, sorry, I'm saying slab, but I mean, I mean raft. And you can check out the required reinforcement from robot. Well, and that's basically it. That's what I wanted to test very quickly. So to recap, we have basically I have explained in this video how to have beams with elastic foundation and how to use this elastic foundation to support a structure. And then I suggested, and this might be incorrect, I need to double check this. I suggested a way of basically having a raft with the beams combined together. That's it. Before I finish, I still need to dive deeper into this and to make sure this works or not, but this was just a food for thought. My point here was to explain elastic foundation on beams. This is a side product of that explanation. Well, and that's it. I hope that you enjoyed the video and it was beneficial for you. If you have enjoyed the video, then please like, share, comment, subscribe, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video.